Simplifying radical expressions. Review. In this lesson, we'll simplify square root expressions by rationalizing perfect square factors in the radicand, and we'll simplify square root expressions by rationalizing denominators that include imperfect square roots. We're about to begin Chapter 8, which has a lot of right triangles in it as we're entering into talking about trigonometry and right triangle trigonometry. And since there's right triangles, then there's going to be some side lengths where we use the Pythagorean theorem that will lead to some square root expressions. So we need to take a moment to make sure that you know how to simplify radical expressions. Hopefully this is a review. If it's not, it's going to be a quick crash course and some things you'll need to know for Chapter 8. And before we start talking about simplifying radical expressions, I need to introduce you or reintroduce you to the product property of square roots. And what the product property of square roots says is that the square root of a product, two things multiplied together, the square root of like A multiplied to B, is the same as the product of the square roots of each of the factors. So as long as we're talking about multiplying things in the radicand, then we can find the square root of each of those factors. And we simplify radical expressions, and we use this property to simplify them so that our calculations match those of our peers and we can compare answers more easily. And we do this so that the accuracy of our work is not compromised by rounding. We're not going to find something like the square root of 5 and round it to the nearest tenth and lose accuracy. Instead, we're just going to simplify that expression in the way that we're going to talk about in just a moment. In order to simplify radical expressions or square root expressions, we'll be needing the product property of square roots, and it's also going to be helpful to have a list of perfect square factors. So I'm going to generate a list of 15 perfect square factors for us to refer to as we're going through some examples here today. And for my list of perfect square factors, I'll start with 1 squared. So 1 is a perfect square. 2 squared would be 4. 3 squared would be 9. I'm just going to continue like that. 4 squared is 16. 5 squared is 25. 6 squared is 36. 7 squared is 49. I'm going to keep going. I'll have 64, 81, 100. I'm going to keep going 5 more. 11 squared is 121, then 144, then 169. 14 squared is 196, and 15 squared is 225. When you see those numbers in your future, they should ring a bell as perfect squares. Sometimes those are important in your calculations. So let's look at how we're going to combine the product property of square roots and this list of perfect squares to simplify square root expressions. So if we want all of our work to look the same when we're done, if we wanted to simplify this radical expression, zoom in just a smooch, then what we're going to do is look for any factors that are perfect squares. In fact, we're looking for the largest perfect square factor in the radicand. And then we'll rewrite the radicand as a product of 2 factors and use the perfect square factor that you identified. So if you don't immediately see one of these numbers as a factor, maybe you're just not sure what all the factors of 98 are, then you can make yourself a little factorization tree and get down all the way to the prime factors of 98. Well, it's an even number, so you know it's going to be 2 multiplied to something. And if either of those numbers can be factored further, we continue factoring until we have nothing but prime numbers left. There's our prime factorization tree. And anytime I have a factor show up more than once, then that means I've got a perfect square factor somewhere in this number. And I'm going to use that perfect square factor to simplify the square root of 98. So let's rewrite this radicand, 98, as the product of two numbers. I think we can all agree that 98 is the same as 2 times 49. So I've not changed anything. I've just broken 98 into its factors, into two factors. And now I'm going to use the product property of square roots from up here. If I have two things multiplied together, that's the same as the square root of each factor. You can see I've just split apart those two factors. That was step 2 here. Use the product property of square roots to rewrite the radical as the product of two radicals. And then I can see that I can simplify this one. I know the square root of 49 is 7. That's the number I can multiply by itself to get 49. So I'll just change this to 7. Now, so no self-respecting mathematician is going to write it like this. They're going to take the number that's not under a radical and bring it out front. The radical comes second. That way we're never unsure of whether that 7 is under the radical or not, just from sloppy writing. The 7's out front, and then the square root of 2 is still in the radical. And I can't simplify that any further, because 2 doesn't have any perfect square factors that I can continue to bring out. So that's completely simplified. Now, it is important to note something that you might be tempted to do. So I'm going to zoom in on this, make a big no-no here. It's important to note that you cannot split up radicals with sums and differences. We have a product property of square roots, but we don't have one for sums and differences. So this will not work. The square root of 64 plus 36 is not the same as the square root of 64 plus the square root of 36. I think just a little quick math will show you that that is absolutely true. 64 plus 36 is 100. And we know the square root of 100 is 10. But if we go in the other direction here, the square root of 64 is 8. The square root of 36 is 6. And if I add those together, I certainly don't get 10. So 10 is not equal to 14. And the square root of 64 plus 36 is not the same as the square root of 64 plus the square root of 36. So I can do it when I have things multiplied together, but it doesn't work for addition and subtraction. So it's important to note that. Let me zoom back out. So let's talk through just a few of these so that you can see how this goes. I'll zoom in on all of these. Let's start with the square root of 80. Now, I know you're looking at 80 and thinking, oh, 4 will go in there. 4 is a perfect square. And it will. But if you don't choose the largest perfect square factor, then you're just going to have to keep doing a little additional work. So like I did before, I'm just going to come off to the side and I'm going to make a factorization tree. Look at its prime factors. So I knew that 4 times 20, and I'm going to break this down a little bit more. I have 4 times 5. That's a prime number. And I could break this 4 down into 2s. But what I'm looking for is numbers that are doubled here. I have a 4 and another 4. So 4 times 4 is 16. So I bet 16 times 5 is 80. And that's going to be the biggest perfect square factor that I can get out of this 80. And I could have done 2 times 2 times 2 times 2, still would have wound up with 16. 16 times 5 is still 80. I've not changed the value, I've just changed what it looks like and broken it into factors. And now I'm going to separate those two factors using the product property of square roots. And I'll clean up that perfect square factor. And now it's simplified. I can't simplify the 5 any further. 5 doesn't have any perfect square factors. Let's go on to this next one. Now, I'm feeling pretty confident about 18, but if I wanted to do the prime factorization, I could. That would be 2 times 9, 3 times 3. Well, I see a prime factor right there. That's the largest, that's not a prime factor. That's the largest perfect square factor of 18. Now, this one's just a little different because I have a number that's already outside of the radical. I'm not going to do anything to simplify that further, but it does need to come along with the expression. So I'm just going to bring that 4 down, but I'm really focused on the square root of 18. So 18 is, I'm going to put the 9 first. I like putting the perfect square first. Doesn't matter. So 4 times the square root of 9 times 2. I'll use the product property of square roots to split those apart. And now I can just clean up this perfect square factor. 4. Square root of 9 is 3. And that 2 doesn't get simplified any further. I'll go ahead and multiply these two numbers that are no longer under the radical. And that 2 stays separate. That's as simple as we can get that expression. There are no other perfect square factors under the radical. Let's look at this example that has an x in it. Don't be afraid of that x. It's just another factor. Again, we have 3x multiplied out in front. I don't need to simplify that further, but I do need to carry it along. For the 50, I bet you can already imagine the greatest perfect square factor there. 25 times 2. And I don't think I'm going to get a bigger perfect square factor than that. If you wanted to continue with the prime factorization, when we end up with these with these prime numbers, I see that I have a double here, which indicates that I've got a perfect square factor. Just squish a little bit here. So I'm going to rewrite 50 as 25 times 2. And I still have that x as a factor as well. So let me go ahead and break these apart. I'm just bringing down the 3x. You'll see I'm not doing anything with that. Square root of 25 times the square root of 2 times the square root of x. That 25 is the only one that I can simplify further. Square root of 25 is 5. And these other two, I can't simplify them any further. So I'm just going to leave both of them under the same radical. I'll pull those back together. And for all the numbers that escaped the radical, or that 5 that escaped the radical, I'll just multiply it with the numbers that were already outside. 3 times 5 is 15. I have that x. And under the radical, I have 2x. And I did want to look at one expression that had a variable that was a perfect square. So even though 5 is a prime number, it won't be simplified any further. If I look at x squared, I know that's just x times x. So it's clearly a perfect square since it's x squared. So I'm going to go ahead and break apart those two factors, 5 times x squared. And this time it's not the number that's going to get simplified, it's this. So I have 2 times, let me just jump over the square root of 5. The square root of x squared is just x. And this 5 that was in the middle stays under the radical. So my final answer is 2x times the square root of 5. So variables can be perfect square factors just like numbers can be perfect square factors. Let me back out. So that's just the beginning here. That's simplifying radical expressions using the product property of square roots. Take a little breath and we're going to flip over and talk about rationalizing denominators. All right, let's go on to part 2 here. This way of simplifying is called rationalizing the denominator. Radical expressions do not appear in the denominator if the expressions are simplified. So if we want to have a simplified expression that looks like all of our peers and we can compare our work, we don't have radical expressions in the denominator. If we do, if we have something like this right here, 4 over the square root of 6, if we have a radical expression in the denominator, we have a technique for changing irrational denominators into rational ones. It's called rationalizing the denominator. Let me zoom in just a bit. And it's kind of a cool technique. To rationalize the denominator of a radical expression, what we're going to do is we're going to multiply this expression by 1. Multiplying by 1 doesn't change the value of this expression, but it will make it look different. It'll simplify it. So I'm going to multiply this expression by 1, but my 1 is going to be constructed in such a way that it changes that denominator into a rational number. I think we can all agree that anything divided by itself is 1. It's really just 1. But the reason I chose to write the square root of 6 over the square root of 6 is because this denominator is the square root of 6. And look what happens when I multiply by a 1 that looks like this. Well, in the numerator, I have 4 times the square root of 6. I'm going to go ahead and write that. And in the denominator, I have the square root of 6 times the square root of 6. And just like the product property of square roots lets me split apart factors, it lets me put them back together as well. The square root of 6 times 6 is the square root of 36. And you can see I've changed that from an irrational number, the square root of 6, to a rational number. The square root of 36 is a perfect square. So I've rationalized the denominator. So I went ahead and simplified all those radical expressions. And the numbers that are outside the radical, I can reduce those just like any other fraction. If I had the fraction 4/6, I would reduce that to 2/3. And I also want to note, you cannot cancel these 6's. This is a 6. This is the square root of 6. They're not exactly the same. So I'm just going to write, you can't cancel the 6's. If they were both under the radical or both outside the radical, I could. But if one's under the radical and one's not, I cannot cancel those. So let me just reduce that 4/6. So 2 goes into 2 4 times, 2 goes into 6 3 times. So that's 2 times the square root of 6 over 3. So this is another one that takes some getting used to. Let's do a few more problems like that. And again, the main thing that we're doing is multiplying by a fancy looking 1 that helps us to rationalize the denominator. These are just the rules mathematicians have for getting all of their work to look the same and not lose accuracy in their answers by rounding. All right. So let's do it with 2 over the square root of 3. We don't want a radical in the denominator. So we're going to change that from an irrational number to a rational one. We're multiplying by a fancy looking 1. I'm going to multiply by the square root of 3 over the square root of 3. I'm just multiplying by 1. That doesn't change the value of this, but we're going to change what it looks like. All right, so in the numerator, 2 times the square root of 3 is just that. I can't combine those together because the 2 is outside the radical and the 3 is under the radical. But down here, I have the square root of 3 times the square root of 3. I can put those together, the square root of 3 times 3. And that's really, here's my numerator, the square root of 9 in the denominator. And once again, I've changed this irrational square root of 3 into a rational square root of 9. It's a perfect square, so that can be simplified in the denominator. The numerator can't be simplified any further, and I cannot cancel these 3's. This one's under a radical and this one's not. Let's look at this next one. See if you can think of what we're going to multiply to rationalize this irrational number in the denominator. We're multiplying by 1, but this is what our 1 looks like, the square root of 7 over the square root of 7. In the numerator, we wind up with 21 times the square root of 7. In the denominator, we wind up with the square root of 7 times 7. You just come down here. 7 times 7 is 49. And I've changed that from an irrational square root of 7 to a rational number because the square root of 49 is really 7. Now you know by now that we can't cancel this 7 with this 7. But I can reduce this. 7 goes into both of these. So 7 goes in here 3 times, 7 goes into 7 1 time. So my final simplified answer is really 3 times the square root of 7. I have 1 in the denominator, but mathematicians would laugh and laugh if I wrote that there. Again, I want to take a look at what would happen if I had a variable as the radicand. Same thing we've been doing. Just going to multiply by fancy 1. It just looks like the square root of x over the square root of x. And as long as x does not equal 0, we're all set. In the numerator, I wind up with 20 times the square root of x. Make sure you keep apart things that are outside the radical and under the radical. And this 2 here, I'm just going to leave it outside. I don't need to simplify that. But then I have the square root of x, and I'm going to put that together under the radical with this other square root of x. And now I have a perfect square factor. The square root of x squared is just x. And anytime you notice that you have numbers that can reduce, it's okay to, I could have reduced the 20 halves way back here if I wanted to. 2 goes into 2 once, 2 goes into 20 10 times. So in the numerator, I'm left with 10 times the square root of x. And in the denominator, I'm just left with x. These x's cannot cancel. One's under the radical, one is not. This last one is pretty busy, so I guess we can go ahead and do one last one. The reason this one is so busy is because there's some things I can simplify that don't have anything to do with multiplying by a fancy 1. Just show you what I mean. So I have that 5x in the numerator. I have the square root of 50 and the square root of x squared. Now already, I can see that there's some things that I'm going to be able to simplify, even without multiplying by a fancy 1. X squared is a perfect square, so I'm just going to simplify that to x. And the square root of 50, I know there's a perfect square factor in there. There's 25 times 2. So let me just do a little cleaning up in the denominator, and then I'm going to worry about rationalizing it. So my numerator stays the same. My denominator, I've got the square root of 25 times 2. That's the square root of 50. And I've got this square root of x squared. I'm going to go ahead and just simplify that. The square root of x squared is just x. You know what? I have an x as a factor in the numerator and an x as a factor in the denominator. Those are just going to cancel right out. I can get rid of those. And now I just have to worry about these other numbers. So I have 5 left in the numerator. In the denominator, I have the square root of 25 times the square root of 2. I don't have a lot of room here, so I'm gonna not separate them, but I think you can see that the square root of 25 is going to become 5, and the square root of 2 just stays there. Gosh, I've got some more canceling I can do. I have 5 is a factor in both the numerator and the denominator. So before I even rationalize the denominator, I've got it down looking like this. Now let's go ahead and rationalize that square root of 2. So we could have done this from the beginning. I'm going to cut to the chase here. The square root of 2 times the square root of 2 is the square root of 4. And the square root of 4 is 2. I could have multiplied by the square root of 50x squared over the square root of 50x squared, but then I just have a giant mess on my hands. So I just wanted to show you that if you see some simplifying that can be done first, it might make the rationalizing the denominator a little friendlier. So we're going to run into a lot of simplifying radical expressions in this coming chapter. There's some additional practice down here for you. We might play a Kahoot in-game where in class where these are the problems. Scooch up just a little bit. So if you do these ahead of time, you'll have yourself a little Kahoot cheat sheet. Number 15 is separate from the other Kahoot problems, but if you want to try that challenge, I would encourage you to do that. So there's not a solution. This isn't technically homework, and this isn't a solution, or this doesn't have a solutions key on Schoology, but I'm going to encourage you to pause the video, complete these 15 problems, and when you turn it back on, the solutions will be on screen for you right here. So go ahead and pause and try that out now. All right, go ahead and see how you did with all of the simplifying radical expressions.